talk a little bit more periodic table before we go over to the periodic trends. In the previous video, we talked about the electronic configuration, and I explained to you that energy increase with the increasing of the main level, because they're getting far away from the nucleus. That means the attraction between nucleus and the electrons are decreasing, so their electrons are more free to move, so it's easy to take out electrons, it's easy to give away electrons because they are far away from the nucleus. Okay, so periodic table organization is the best thing that happened in chemistry because they are organized so well. So classification of the elements. In 1829, the German chemist Tauberring observed that several elements could be classified into groups of 3 or triads. All 3 elements and triads showed a very similar chemical properties and orderly trend in physical properties. Organizing the elements, in 1865, Newland suggests that the 62 known elements be arranged into groups of 7 according to increasing atomic mass. His theory was called the law of octaves. So he proposed that an 8th element would repeat the properties of the first in group. So let's go and talk about Mendeleev. This is my favorite scientist that was part of the group that organized the periodic table. And why he was the most famous of those scientists? Because when you talk about periodic table, you always talk about Mendeleev. It's not because he was Russian and invented the vodka. No, it's because he was so smart that I will tell you how fantastic he was. Mendeleev proposed that the properties of the chemical elements repeat at regular intervals when arranged in order of increasing atomic mass. He arranged his periodic table in columns by the formula of the element's oxide first. And then he left blank some space over here and said, okay, we don't know this element yet, but that will be found. Someone will discover this element, and this element will have these characteristics and will fill this space over here. This is why everybody talk about Mendeleev instead of all the other scientists that work with the periodic table. Mendeleev noticed that there appeared to be some elements missing from the periodic table. That is the most fantastic thing over here, right? Imagine that you're creating the periodic table and then you have a blank space and say, like, I don't know this element, but someone is going to discover this and will be filled in this space over here. So he was able to accurately predict the properties of the unknown element X silicon in 1869. And it was discovered, look at this, in 1886 as germanium. So he could say the atomic mass and the melting point, formula, everything. So this is what he told. Look at this, the atomic mass. He predicted the atomic mass should be 72 atomic mass units, and the color should be gray. Look what they discovered. 72.6 atomic mass. Density, he said it should be 5.5, and he was discovered 5.32 grams per milliliters. Melting point, he said that it should be very high, and it is. And then he gave the formula, yeah, pretty close, and density pretty close, actually exactly the same. So boiling point, he got very close. So he was very smart. This is why we talk about the Mendeleev. So then we have the noble gases. The periodic table was expanded by one group at the far right of the periodic table with the discovery of argon in 1894. Helium, neon, krypton, xenon, and radium were subsequently discovered in the next 5 years. These were originally called the inert gases. Starting in the 1960s, several compounds of xenon and krypton have been made, and then the thermal noble gas is currently used. So before we call it inert because they was like considered that they will not react it. They don't react it. So those elements are so stable that they don't need to react it. But since they starting several compounds of xenon and krypton, so that they could change the name now to the noble gas. So they don't tend to react because they are stable. So the periodic law concept mostly discovered that the nuclear charge increases by 1 for each element on the periodic table. He concluded that if the elements are arranged by increasing nuclear charge harder than atomic mass, the trends on the periodic table are better explained. So the periodic law states that the properties of elements recur in a repeating pattern when arranged according to the increasing atomic number. With the introduction of the concept of electron energy levels by Bohr, the periodic table took the current arrangement. So the arrangement that you already know. So we have a level of energy, so we have the groups, right? So in the past we used 1A, 2A, 3A, 4A. Now we use 1, 2, 3, 4 up to 18. So that is the groups that we have. So groups are the vertical columns in the periodic table. Over here, that is the group. And groups contain elements with similar chemical properties and are sometimes referred to as family. And then we have periods, which are the horizontal rows in the periodic table, and elements in the periods show a range of properties. So if you go in the first group, when you do electronic configuration, for example, hydrogen, so we have 1s1, and if you go to lithium, so 1s2, 2s1. So see, 1 and 1, that is the valence electrons. So if you go to sodium, 1s1, 1s2, 2s2, 2p6, 3s1. See that all the elements end with just one valence electrons. Valence electrons are the electrons located in the last shell of energy. Okay? So the representative elements of or main group elements are in the group A or group 1. The transitional elements in the B groups. Remember that we saw here A, so and then we have a B that I said, oh, before we use letters, so now we use numbers. So that is what it refers over here. The inner transition elements are found below the main body of the periodic table. They are also referred as heart or elements. So the inner transition elements are divided into lanthanides and actinides. And we have alkali metals, no, group 1, alkaline earth metals, group 2, we have the noble gas, and the halogens, which is in the group 17, fluorine, chlorine, bromine, iodine. All these elements are the noble halogens, okay, not noble gas. Noble gas is group 18. So let's go over to, again, just to explain to you how great are the periodic table. So let's look to the group 1. All the elements has the same number of electrons and they're furthest out from nucleus, which means that all the atoms in this group have only one valence electrons, as I explained it to you. And here you can see using the Bohr model again. So one electron in the last shell. Of course, hydrogen has just one level of energy. So valence electrons. So the valence electrons in this group 2 will be 2. So if you look to the element group 2, they all have 2 electrons in the valence shell. If you go to group 13, 3, 4, 5, 6, 7, 8 valence electrons. Okay? Several families have common names. Group 1 are the alkali metals, as I said before. Group 2 alkaline earth metals, and group 17 are the halogens, and group 18 the noble gas. There are 18 groups of the periodic table on the periodic table. American and European conventions had different designations for the groups. Both use A and B designations with Roman numerals, but the A's and B's were different from each other. So in 1985, International Union of Pure and Applied Chemistry, we already talked about that IUPAC before, proposed a new numbering scheme. So in it, the groups are assigned numbers 1 through 18. Okay? So now another thing that periodic table can tell you is the trends. So the atomic radius decrease as you go up, and it decrease as you go left to right across the period. And they're gonna tell you how that works. Look at the first level of energy. I'll put it here, this is like a nucleus, okay? Oh, let me get back. So I have just one level of energy. If you go to level 2, I have 1, 2, 3 level, 3, and the 4, 1, 2, 3, 4, and 5, 1, 2, 3, 4, 5, and 6, 1, 2, 3, 4, 5, 6. See how I'm getting bigger? Because I'm increasing the number of levels. It's exactly what happened to us. When it comes to winter, if you go to South Carolina, North Carolina, that it's so cold compared to Florida, you're gonna use a jacket, and you put one more, and the socks and everything, so you're getting bigger. It's the same thing here, so you don't need to memorize. So this is why when U goes up, as here it's saying, you decrease the radius, but if it goes down, you increase the radius. Okay, so the size of the atoms. Oh, okay, so but what happened in the same row over here? So if you get this row over here, look at this. They have the same number of levels too, right? But look at this. What happened over here is increasing the atomic number. So as soon as I increase the number of protons, what happened? So we increase number of electrons as well, right? Because protons and electrons has the same number if we are ground state elements. So the attraction between the nucleus and electrons will be bigger. So remember, atom is full of empty space. So if this attraction is increasing, what happened? This empty space is getting smaller. Oh, sorry. And then I got the pen again, sorry. So the pen disappeared, and then, okay. So I'm increasing the atomic number. So I'm decreasing this space over here. So it will be like here. If I increase a little bit more, it will be like here, and it goes on. So this is why it's getting smaller, okay? So you can, if you want to memorize, it's up to you, but if you understand the concept, like of the energy, so increasing the attraction will decrease the size, you don't need to memorize, okay? If you look over here, it's the same thing. So we increase, and when you go down to the group, and the U decrease when you go from left to the right. Okay? So atoms get smaller as you go bottom to top on the periodic table, because as you travel up a group, there are fewer energy levels on the atom, as I explained it before. Atomic radius decrease as you travel left to the right across the periodic table, because the number of protons in the nucleus increase. So these protons draw the energy levels and their electrons closer to the nucleus, so we increase the attraction. Okay? So, but what happened with the ions? Look at the fluorine. If I add an electron, what is going to happen over here? So the number of electrons will be different from the number of protons, right? So I have more electrons than proton. So I will get bigger, because remember, the attraction exists, of course, but if I have more electrons over here, so what happened also increase the repulsion between those over here, between levels of energy, because I have electrons here and electrons here, more repulsion over here, so then we get bigger. But if you take out an electron, so we get more positive, so we increase the power of the nucleus. So if you increase the power of the nucleus, so more positive charge will attract more the negative charge. So this is why we decrease when we remove an electron. Okay? So this is an example over here. So you can just encourage you to pause your video and try to do by yourself those elements here, and then put in an order who is the biggest, who is the smallest. They say the increasing order, so go to the smallest to the biggest. Okay, so just pause your video and go over and try to do by yourself. So we can go to the periodic table. Let me get a periodic table over here. Okay, not this over here. So if you go over here in the periodic table, you can go to the elements that we had there. Nitrogen, again, my pen. All the time that I get back to the slides, the pen disappear. So I have nitrogen over here, and I have lithium over here. So they are in the same level, but I know nitrogen is smaller because I'm getting more electrons, more protons, so it's smaller than lithium, right? And then I have magnesium that is bigger than lithium and nitrogen. And what else? I have potassium. This is the biggest one, right? So, and the smallest one will be nitrogen. So we have 4 elements, right? So we have lithium will be this, nitrogen will be the smallest one, and then we have the potassium as the biggest one. If you only have nitrogen, lithium, magnesium. Let's go back to our problem over here. So what do you have here? So the smallest one will be lithium. No, the biggest one will be potassium, right? So we have all this, and the smallest one will be nitrogen. So we have a nitrogen here, and we have potassium over here. So it could be A or D. So we need to go over magnesium and lithium. So lithium is in the group 2, while magnesium, let's go back there to show you again. So magnesium is in the group 2, while lithium, no 3, sorry, and lithium is in group 2. So lithium is smaller than magnesium, right? So lithium is smaller than magnesium. So we have a nitrogen, lithium, magnesium, and potassium, okay? So metallic character is the degree of metal character of an element. So metallic character decrease left to right across a period, and from bottom to top in a group, okay? So we'll decrease in the bottom to top, like the size. The size decrease in the bottom to the top, and the metallic character decrease left to the right. So when I get it to the right, it's increasing the size. So the metallic is decreasing the size, so it's decreasing also the metallic character. So it goes over the same way. Metallic and atomic radio goes in the same way. Okay. Properties of elements. Since the properties of the elements follow regular patterns, we can predict the unknown properties of an element based on those around. Look at this. Francius is missing from the table below. We can predict its properties. The atomic radio of Francius is greater than 0, right? 0.2 166 nanometers. Density will be greater because look at this. What's happening over here? I'm increasing. Look at this. Atomic radius is increasing. So I know this element will have atomic radius bigger than 266 pm. And I know the density is also increasing, so it will be bigger than 1.87 grams per milliliter. Melting point is decreasing, so I know that it will be smaller than 28.4 degrees Celsius. While atomic mass is increasing, so I know the atomic mass will be bigger than 132.91. Okay? So of course there will be some things that will not follow this, like if you see the density of potassium, look at this, is a little bit smaller than the sodium. So small irregularities in group trends are not unusual. So we're gonna find something like that, okay, with other elements. But in general, they follow the same pattern, okay? So members of a group of family have similar chemical properties. All the alkali metals have oxides of the general. So alkali metals, lithium, sodium, potassium, rubidium, cesium, and francium, okay? So they all have the same. So the formula for chloride, the chloride of calcium, is calcium chloride. What is the formula for the chloride in barium? The general formula, I will grab this. So if you go to calcium, look at this. Calcium is in the group 2. So that means they have 2 electrons. They're metals, so at the positive they tend to lose electrons, okay? Metals, group 1 and 2 tend to lose electrons, okay? And they will lose 1 electron if it's in the group 1 and 2 electrons if it's in the group 2. Calcium is in group 2 will lose 2 electrons, so this is why it's positive, while chlorine is in the group 17. They are halogens, so they need 1 to have 8 electrons to comply with the octet rule. So that means if all the element has 8 electrons in the last shell, they will be stable like noble gas. So when you go to group 17, they need 1. If you go to group 16, they need 2 electrons to be happy. 15, they need 3, and so on. So -1. So if you cross the charts, look at this. Calcium, you don't carry the signs, okay? And you don't use 1, remember? So in the chlorine, it'll be 2, okay? So this is why it's calcium chloride. The same thing with the barium. So it's a group 2. So it has +2, chlorine is -1, so we cross the charge and we have this. Good? So recall the order for filling sublevels of electrons. That is important. The periodic table is organized according to the blocks as I talked before. So we have block S, P, and D, and F. So it's easy to do the electronic configuration over this. So if you go to electron configuration of sodium, you can use the periodic table or you can use FBAL, like the construction principle or building principle. So you can use small electron configuration of the reduced electron configuration. So the preceding noble gas with atomic number less than sodium is neon. So if you take out this is the electronic configuration of neon. So you're going to use this and this. So that is the electronic configuration of sodium. You can go over another elements over here. So, and you're going to do the same. Always look to the electronic configuration and see which elements, which noble gas we have. So you represent the noble gas, so you don't need to write everything. And then go to keep it going. So here write the electron configuration as follows. Okay. So valence electrons, already talked about this, are the electrons in the outermost principal energy level of an atom. These are the electrons that are involved in a chemical reaction. I like to think about this as the money that you can use. Okay, it's not your savings. You're the money that you can negotiate. So the valence electrons are the s and p electrons beyond the noble gas core. So remember that I did the electron configuration for group 1. All those elements has 1 valence electrons, and this has 2 valence electrons. Okay, this will have 3 valence electrons, 4 valence electrons, and 5 valence electrons, 6 and 7 valence electrons. The Roman numeral in the American Convention indicates the number of valence electrons. Elements have 1 valence electrons, elements have 5 valence electrons. Now we're going to use number 1 to 18. So when you get a tens, you don't look to the first number, just the last number. So 18 has 8 valence electrons, 17 7, 16 6. So when you use IUPAC designation, so numbers, the last digit indicate the number of valence electrons, as I said before. And one very important thing here is how you can represent those electrons, the valence electrons. So we use electron dot formula. So you use the symbol of the element, and then you use the valence electrons. So here I have 2, 4, 6, 8 valence electrons. Okay. So I'm using phosphorus as an example, so we can show how to represent the valence electrons. So here 1 valence electrons, 2, 3, 4, and 5. You cannot do this 1, 2, 3, 4. This is wrong. Okay, you cannot do this 1, 2, 3. Wrong. This is how you distribute around. So first you're gonna round the elements. So I have 1, 2, 3, 4. So now I have 6. So we form pair 5. Okay, and I have 6. So we form pair. But at first you put a single electrons around the element. So the ionization energy of an atom is the amount of energy required to remove an electron in a gaseous state. Just remember, if I'm close to the nucleus, I will have high energy or lower energy. Just think. Will be higher, right? If I want to take out the electron, I will need high energy to take out because they are so attached to the nucleus, because the attraction is bigger. But if they are far away, so the energy that I need to take out this electron will be lower because they are far away from the nucleus. So in general, the ionization energy increases as you go from the bottom to the top. Of course, because they are close to the nucleus, because I'm getting smaller. So if I'm getting smaller, look at this. So it's close to me. It's like if I'm holding a bar of gold, and if it's close to my chest, it's really hard to take out from me, right? But if I'm open arms and the gold bar is far away from my chest, and I'm holding only one hand, it's really easy to take out from me because it's outside of my string, which is close to my chest, right? So if you look at this, ionization energy trend is exactly like this. Will increase if you have a smaller atom, right? So this is why I draw those little atoms over here, and the boy on the right is trying to remove the electron, but it's so hard because the atom is small and almost a full shell over here. So this will not give away this electron so easily, okay? Electronegativity corresponds to the ability of an atom nucleus to hold the electrons involved in the chemical bond. So that means if I have more electrons I will attract more. Okay, so if I have fluorine that has 7 electrons and a valence electron, it just need 1 to be happy. So of course we attract easily, while the metals normally lose electrons. Okay, so metal ionic charges, metals react by losing their valence electrons when forming ions. I'm doing so they achieve the electron. Why they do this? Because if they give away electron, they will achieve the electron configuration of the nearest noble gas, so they'll be stable. So if you look to here, so first it holds only 2, and here can hold 1, 2, 3, 4, 5, 6, 7, 8, and here can hold also 8 in the third level, but only have 1. So imagine if I lose this one over here, the last shell will be the second one. So and then we have only this electronic configuration being like the noble gas, okay, similar to neon. So similarly, non-metals can gain electrons. All the elements in group 13 to 17, they can get electrons. So 15, for example, they form -3 ions, 16 -2, and group 17 -1. See, it's only 18 minus 17. Oh, sorry, 17 minus 18, because this is the noble gas, because they all want to be like noble gas to be stable, will be -1. And here 16, so 16 minus 18, so -2. See, okay, it's easy to find out. So in general, the charge of an ion from a metallic representative element is equal to the group or family. So the charge of an ion from a non-metallic representative is determined as follows: charge, family number, minus A. But since we have, we only look to the last number, okay? So, or you're gonna use a minus 18, so it would be 15 minus 18. So if you use only the last number, it will be 5 minus 8, so -3, and it goes on. Okay? So it's easy to find. Group 1 would be +1 is metal, group 2 +2, and here are the non-metals, -1, -2, -3. So some elements will change a little bit, okay? But now these are fixed, so they will not change. So the number that you see over here are the charge that you see over here. So isoelectronic series, atoms and ions with the same electron configuration are isoelectronics. So we have ions that can have the same electronic configuration for the other ions. Or for example, over here, so we have phosphorus. So negative charge means that the element gained electrons, so you need to add 3 over here, so it'll be 6, right? So now I have the same electronic configuration of, so if you go to the periodic table and it goes and this, look at the numbers in the third period, we have noble gas over there, argon, right? So it's similar to argon. You can do the electronic configuration using the F-ball or the periodic table, okay? So I already explained to you the electron configuration before of ions, but I want to enforce this. So when we write the electron configuration of a positive ion, we remove 1 electron for each positive charge. So we go to the last level of energy and we take out, so 1 electron. So now I have this electronic configuration, which is similar to neon. So now again we have we have more 2 electrons. So we're gonna add in the last level where I have space. So 4 plus 2 is 6. This I have the electronic configuration as the neon, similar to the neon. Okay, so don't forget that. So the elements in the periodic table are arranged by increasing atomic number. The elements have regular repeating chemical and physical properties. The periodic table can be broken down into groups or families, which are columns, and periods or series, which are the rows. Atomic, radial, and metallic character increase as you go from bottom to top and from left to right the periodic table. Periodic table can be broken down into blocks. where a certain sublevel is being filled. Valence electrons are the outermost electron and are involved in a chemical reaction. We can write down electron dot formula for elements which indicate the number of valence electrons. Ionization energy is the amount of energy that is required to remove an electron from an atom in the gaseous states. Just remember, if it's close to the nucleus, a small atom will require a lot of energy to remove an electron. So we can predict the charge on the ion of an element from its position on the periodic table. So in accordance with the group, so +1 and +2 in the group 1 and 2 for metals, and no metals will be negative. Okay? That's it. That's all. Bye for now.